Alright, so Year 12 we are using de Moivre's theorem to solve equations. So if we have things like, for example, equations of this form, z to the power of n is equal to a, where z is a complex number. We can use using de Moivre's theorem. Alright, don't keep noise out. So what we need then is in polar form, because that's what in de Moivre's theorem is about. Then z would be r cis theta, and what we need to do is express a, whatever a is, we need to express it as r1 cis alpha, and the alpha is using alpha rather than theta. So we know these two angles are not the same. So if that's the case, z to the power n equals a becomes cis theta to the power of n excuse me, equals r1 cis alpha. And then if we use de Moivre's theorem here, it's r to the n cis n theta equals r1 cis alpha. And so then from that, if these two things are equal, then r to the power of n and r1 must be the same. So r to the power of n equals r1. So we can work out what that is. And the other bit, the cis bit, so cis n theta has got to equal cis alpha, and so that means that there's a relationship between these two. So n theta then is related to alpha, but in general terms, we can keep going round and round in circles. So n theta would be alpha plus 2k pi, where k is
what's k?
k is an integer, or positive integer.
Yeah.
And so from that then, theta will be alpha plus 2k pi over n. And so once we know what our r is and our theta is, we can get our solutions. Now this n or the k I should say, not the n, the k, because there's different numbers that we could do. What we need to do is we need to choose values of k until the required number of solutions. Found. Now, what that depends on whatever this n is up here. So if that's n to the power of 4, from what we already know, if you got a polynomial that's power of 4, how many factors, how many solutions would there be? 4. So here we need to choose 4 values of k, and when you did that you would go 0, 1, 2, 3, not just random ones. Alright, so we'll have a look at
What is that? Say at the top.
which,
Right.
where,
That one?
this one.
Yeah.
So z to the n equals a becomes, I've left the c out, Toby, can't spell.
Yeah.
That's why I'm
Well,
not,
give her a-
that's why I'm not an English teacher, Toby. Becomes. Alright, so let's have a look at an example, or a few examples. Alright. So, example, e.g. solve z cubed is equal to 1. Alright. So, at the outset that would seem pretty obvious. Z is 1. That's only one solution. But in terms of complex numbers, it's possible for us to get 3 solutions. Alright, so here where it says choose values of k until the required solutions are found, because this is cubed up here, we will need 3 values of k. Alright, so first of all, if z is equal to cis theta, and 1 is equal to 1 plus 0i, which is 1 cis 0. Because it's 1, sine of 0 is 0. Then what we do is we relate these two things together with the cubed. So if z cubed is equal to 1, then cis theta cubed is equal to 1 cis 0. And so r cubed cis 3 theta is equal to 1 cis 0. So that's equivalent to this line that I've got here. And so our magnitude bit, or our r bits, have got to be the same, so r cubed has got to equal 1. And from that also, our angle part, 3 theta, is got to equal this angle here, which is our alpha, plus 2k pi. Oops, put the alpha in. zeroing. All right, over here, if r cubed is equal to 1, r's got to be 1. Over here, we need to divide by 3. 0 plus 2k pi over 3, which of course simplifies in this case. Not always going to simplify down, just not necessarily always going to get 0, but this one 2k pi on 3. All right. So now that last bit we've got to do is choose values of k until we get the required numbers of solutions. All right, so because it was a cubic up here, we need 3 solutions. So we choose 3k values. All right, so the 3k values, again, always make it easy for yourself. So k equals 0, k equals 1, and k equals 2. Always go in a sequence. All right, so the first one, when k is 0, actually I haven't put that together, have I, in the final. In this form here is z. So these two things together give us our z. So I should have done that, which I neglected to. So therefore z equals r, which is 1, cis of my theta, which is 2k pi over 3. And now we put k equals 0, 1 and 2 in here. Now have a look. So when k equals 0, z is 1 cis 2 times 0 times pi over 3, which is 1 cis 0, which of course is 1. So that's one of our solutions. The next solution is when k is 1 cis 2 pi on 3. That's all good. The next one equals 1 cis 2 2 to 4, 4 pi on 3. Now, we need to pay attention to our argument. And the domain of our argument has got to be between negative pi and pi. So this one here, 4 pi on 3, it's too much, isn't it? 4 pi on 3 is over here.
Yeah, it does. Okay. So we do.
So we need to
negative
negative 2 pi on 3.
What's that? 2 things.
So that one there,
10.
1 cis negative 2 pi 3.
10.
Alright. So hence we've got 3 answers, 2 of them complex numbers. So if you wrote those complex numbers out and you put the 3 of them together and multiplied them out, so use rectangular or Cartesian form and expanded those brackets, you'd end up with the 1. Yes, no, maybe?
Yeah.
Alright, so up until now we've just been working like with real numbers. And so z cubed equals 1, we go, well, z has to be 1. can also get some complex numbers where when you multiply them together,
So
you
you
get one.
always do k is equal to 0, 1, and 2.
Oh, if you're after 3, that's what you'd do, yeah. You always,
So if you're
always
after-
just go in sequence,
But if you're after 4, go 0, 1, 2,
2,
3.
3. So if I then went another one, k equals 3, all I'm getting now is I'm starting to repeat. So if I substitute k equals 3 into this, I will end up with, what do I end up with? I end up with 1 cis 6 pi on 3, and 6 pi on 3 is 2 pi. Cis of 2 pi is the same as cis of 0, isn't it?
Yeah.
So I'll now just start to repeat the possibilities like spinning around. You just keep it spinning around and you end up in the same place.
Yeah.
So you always start at 0, then go 1, 2, 3, however many you need. All right. All right. So you can also use this with something like this. Something that is. So z squared, for example, equals 1 plus I.
Is that to 2?
Yep. So z squared, 1 plus I. So again, we're working with z is r cis theta. So z squared is r cis theta, and we're going to square it. 1 plus I, because I've prepared one earlier, 1 plus I is square root of 2 cis pi on 4. So we've again got, and of course square root of 2 is 2 to the half, which is going to be index form for your, this is going to be handy later. All right, so that equals 2 to the half cis pi on 4. This one here, the Moivre's theorem says r squared cis 2 theta is equal to 2 to the half cis pi on 4. And so now we can split it, our r part. So r squared equals 2 to the half. So if r squared is 2 to the half, what's r going to be? 2 to the
1. No, 4.
1 over 4?
Yeah.
1 over 4. Just got a square root again. Square root to get rid of that. Square rooting is power of half, half times half. Quarter. Then the other bit, it's got to be the same. The 2 theta, it's got to be pi on 4 plus 2k pi. And theta then is pi on 8 plus k pi. All right, so going back to here, the z's that we're looking for is 2 to the 1/4 cis pi on 8 plus k pi. How many solutions do we need? 2. So we choose k equals 0 and k equals 1. So k equals 0, k equals 0, we've got z equals 2 to the 1/4 cis pi on 8 plus 0. Which is just 2 to the 1/4 cis pi on 8 is one of our solutions. The other solution, 2 to the quarter cis pi on 8 plus 1 theta plus 1 pi, I should say, equals 2 to the quarter cis 9 pi on 8, which is too many pi's. Too many pi's, so yeah, it's negative 7. Alright, 9, there's 8 eighths. So 9 eighths is one there, and how many we got in there? We've got 7. So final answer, 2 to the quarter cis negative 7 pi on 8. All right. Anything so far? Now, there is another way we can look at this. So, this next example would be another way of looking at this. So, these two examples that I've done so far, it's been quite easy to express this here as a complex number in polar form. If you don't have something that's quite so easy to express in polar form and the power's not too high, you can use the following method. So we want to solve z squared equals 5 plus 12i. And if we say using, no, I can put it there. All right, so if the power is not too high, like this one's only squared, oops, what we can do is we can say, okay, because the numbers that we've got here, to put it into polar form, it's not going to be, you know, nice and easy like these, what last two were, with exact values. So what we can do is we can say use z equals a plus bi, and then find out what a and b is in the end. So what we can do, and then we can find what z is. So if I do that, then z squared would be a plus bi times a plus bi, wouldn't it? Yes, it would. Then I can expand this. A times a is a squared, a times bi is a bi. And then I've got another one here, so I've got two of them. B times b is b squared, I times I is I squared, so that'd be minus b squared there, wouldn't it? So now what you can do is you can equate coefficients, or equate real and imaginary parts to be more correct in terms of what we're doing. So the real part, so I've got a squared there and negative b squared, and that's got to equal 5. For the imaginary part, I've got 2abi, and that's got to equal 12. AB's got to be equal to 6. What I'm going to do now is I'm going to make B the subject and say that's 6 over A. And now I'm going to take that, take this here, and I'm going to put it in here. So when I do that, I get a squared minus 6 on a all squared equaling 5. So I get a squared minus 36 on a squared equals 5. Don't like that a squared on the bottom, so I'm going to times everything by.
A squared.
Yep, and when I do that, I get a to the 4 minus 36 equals 5a squared. And then I bring it all to the one side, and I get a to the 4 minus 5a squared minus 36 is equal to 0. Now what? Two numbers that multiply to give me 36, add to give me, or negative 36 I should say, and add to give me negative 5. Four and 9. Yes?
Yeah.
What's going to go in front of these brackets? A squared, correct, because we've got to get a to the 4. So I could have used that technique where I let something equal a squared and gone through that technique. Remember that we did methods.
Yeah.
Alright, but I've shortcutted that. Is that alright? Shortcut it? Alright. So, now we have now it says a squared minus 9 could be 0, or a squared plus 4 could be equal 0. So a squared could be 9, so a could be plus or minus 3. What about this one over here? What do we know about this a? It's got to be a real number, doesn't it? That a there's got to be a real number. Can I get a real number out of this? No, I can't. So a must be real. Too many wiggles for that. I get complaints again about my writing. So a must be real. So no solution from this. So that means there's two possibilities for a. It could be positive 3 or it could be negative 3. And we need to split that up because, remember, our b is 6 over a. So there's going to be two possibilities for b, one corresponding. So when a is equal to 3 or a is equal to negative 3, when a is equal to 3, b is 6 on 3, which is 2. But when a is negative 3, 6 on negative 3, which is negative 2. So our two solutions are there and there. So our solutions, z would be 3 plus 2i, or z would be negative 3 minus 2i. Would be our two solutions, and it's z squared, so we're expecting two solutions. Alright, anything about that technique? Alright, so if its power's not too big, you can use that. When something's difficult to put in polar form.
Otherwise, would we use the polar form?
Otherwise, you would use the polar form, yeah. Because here I only had two brackets, right? You know, if it's z to the 5, and you've got 5 brackets to expand, that's going to be very messy then. So you wouldn't use this method for something like that. All right. Any other questions? No. All right. Well, that's it then. 4G stuff.